In the world of electronics, most components have these really strict rules. You push them the wrong way, apply voltage backward, and poof, they break. But what if I told you there was a component that does its most important, most brilliant work precisely at what should be its breaking point? Well, today we are talking all about the Zener Diode, a true engineering marvel that is designed to thrive in reverse.
Okay, so here's the game plan. We're going to start with the basics of how a regular diode works, as a one-way street for electricity. Then, we'll look at what happens when you push it too hard and it breaks. After that, we'll introduce our hero, the Zener Diode, really dive into its unique superpower, and finally see how it uses that power out in the real world.
All right, so before we can really appreciate what makes the Zener so special, we've got to go back to basics. We have to understand the component it's based on, the standard everyday diode. So think of a regular diode, like a one-way street for electricity. Current can flow through it super easily in one direction, but if it tries to go backward, nope, the road is completely blocked. It's like a check valve for electrical current, and this simple function is just absolutely fundamental to pretty much all modern electronics. So how do they actually build this one-way street? Well, it all starts with two different kinds of semiconductor material. On one side, you have what's called the P region, and it's full of positive charge carriers that we call holes. And on the other side, you've got the N region, which is packed with negative charge carriers, our good old friend, the electron. Now, here's where it gets really interesting. When you bring these two materials together, the electrons from the N side immediately rush over to fill in the holes on the P side. And this creates this neutral zone right in the middle called the depletion region. This region acts as a barrier, and it stops any more current from flowing. So our one-way street now has a gate, and it's firmly shut. So, to get traffic moving again, we have to apply a voltage, which we call a bias. Now, if we apply that voltage in the forward direction, we're essentially pushing the electrons and holes toward that barrier, causing it to shrink, and voila, current can flow. But if we apply the voltage in the reverse direction, we pull those carriers away from the barrier, making it even wider and keeping that current blocked. Okay, so we've established that a diode is designed to block current when it's hooked up backward. But what happens if you just keep cranking up that reverse voltage? What if you really, really push against that closed gate? Well, every diode has its limit, and that limit is known as the breakdown voltage. See, under normal reverse conditions, only a tiny little bit of current leaks through. But if you push past that breakdown voltage, something pretty dramatic happens. The floodgates swing open, and a huge rush of current suddenly pours through in the wrong direction. And this, of course, brings up a really important question. How does a component that is specifically designed to block current suddenly fail so completely? Well, it's this crazy chain reaction called avalanche breakdown. Basically, that super high reverse voltage gives a few stray electrons so much energy that when they smash into an atom, they knock even more electrons loose. And those new electrons get energized and do the exact same thing, creating this exponential cascade, an avalanche of current that for a standard diode usually destroys it. And this graph right here, this is called an IV curve for current voltage. It shows you the exact moment things go wrong. The horizontal axis is voltage, and the vertical is current. As you can see, as we increase the reverse voltage to the left, the current stays near zero. But once we hit that breakdown voltage, that VBR point, the current just plummets downwards. For a normal diode, that's game over. But here's the twist. What if that failure, that catastrophic breakdown, wasn't a bug, but was actually a feature? And that, my friends, is where our hero component, the Zener Diode, enters the picture. First things first, how do you even spot one? Well, in a circuit diagram, it has this unique symbol. See those little Z-shaped squiggles on the line? That's your clue that this isn't your average diode. It's designed to do something really special. And that gets us to its whole reason for being. A Zener diode takes that destructive avalanche breakdown we just talked about and turns it into a controlled, predictable, and incredibly useful event. It's literally designed to live and work in that breakdown region without getting damaged. Okay, this slide right here is the big aha moment. On the right, you've got the Zener's IV curve, and on the left, standard diodes. Now, look at the top right part, the forward bias region. They look almost identical, right? But check out the bottom left, the reverse region. It's a completely different story. Instead of a gradual, unpredictable breakdown, the Zener has this super sharp, perfectly defined vertical drop. And that predictable precision, that's its superpower. So let's zoom in on that IV curve and really break down what's happening when this thing is working its magic in reverse. So here's the full picture. The top right area, quadrant I, that shows what happens when it's forward biased with positive voltage. The bottom left area, quadrant 3, is the reverse biased region, and that is where the Zener truly shines. Yeah, it's really important to get this straight. In the forward direction, a Zener is, well, kind of boring. It just acts like a regular old diode, turning on at about zero point 0.7 volts. The whole reason we use it, the real action, is all about what happens when we hook it up backward.
And this is the absolute key right here. Every single Zener diode is made to break down at a very specific reverse voltage. We call this the Zener voltage, or just VZ. This is a diode's most important stat. A 5.1 volt Zener will always reliably break down at exactly 5.1 volts. So as soon as reverse voltage hits that special VZ number, the Zener kind of turns on, but in reverse. And here's the magic. It clamps the voltage across itself at exactly VZ. Even if the current flowing through it changes wildly, the voltage stays locked in place. It becomes a rock-solid voltage reference.
Okay, so in a perfect world, in a textbook, that line at VZ would be a perfect vertical drop. But in a practical, real-world Zener, there's a tiny bit of a slope. That just means the voltage might change by a few thousandths of a volt as the current changes, but for most jobs, it's incredibly stable. So this amazing ability to just hold a constant voltage, it isn't just a cool party trick. It's actually one of the most useful functions in all of electronics. So let's look at the Zener's main job, voltage regulation. Yeah, its number one job is voltage regulation. If you've got a shaky or unstable power source, you can use a Zener to create a perfectly stable reference voltage. This is absolutely critical for power supplies, for protecting sensitive parts from voltage spikes, and for precisely shaping or clipping signals in a circuit. It really is like the electronic version of a pressure relief valve. And that leaves us with this really fascinating idea to think about. The Zener diode teaches us a powerful lesson, that sometimes the most brilliant engineering solution isn't about preventing failure, but about designing it to happen predictably, and then harnessing it to create something incredibly useful.